Welcome back, everybody. We are going to continue with Chapter 5. So this is Chapter 5, Part 2. We're talking about variability. And specifically, we were up to this point last time. We talked about range, deviation. We got to the sum of squares. Now, today we're going to talk about the standard deviation. But to get to that, we need to do a couple of steps. And we'll get to that in just a minute. Let's do a review question first and then remind us of where we are. So this is a review question. Here we go. Whoops, there it is. If I measure fun on a scale from 1 to 10, I'll probably get what kind of data? You would get ordinal data. That gives you ordinal data. Remember, we're not sure. we know that as the numbers go up, that means more fun is going on, but we can't be sure the amount of fun between 3 and a 4 is exactly the same amount of fun as between a 4 and a 5. So we get ordinal data. All right. Here's where we left off. So our job is to get to standard deviation. That's what we want to do. Whoops, sorry, I pushed the wrong button. There we go. Come on. All right. Sorry. Here we go. What we've done is we've gotten the deviation and we've gotten to the sum of squares. The deviation and the sum of squares. So let me show you on a different one what that looks like. Here we go, right there. Deviation and the sum of squares. Now remember, the deviation was just x minus the mean, and the sum of squares is you square each of those deviations and you add them up. That's the sum of squares. All right, but why are we doing this? What is the point? Why are we trying to get all this done? The entire point is to figure out how weird is Ricky Martin. We want to know how strange is one person out of the group. And what do I mean by how strange is Ricky Martin? Let's go to the data that we've been dealing with this whole time, which is, let's go back to Menudo. So this is the Menudo data, and this is what we've been looking at already, right? Remember, these are all of them. These are all of the members of Menudo, all of them that have ever existed. And you remember we were looking at different pieces of data, so I'm going to move this over just a little bit. So I'm going to, let's go ahead and look at these by name. And I am going to freeze this so that we can see things a little bit better. Okay, and then freeze it there. Okay, good. So here are the people's names, all right? All the different members of Menudo. The most famous one is Ricky Martin. So here is, where are you, Ricky? There you are, Ricky Martin. Okay, Ricky Martin. That's Ricky Martin. And remember, we've been looking at tenure, meaning how long they were in the group. So Ricky Martin was in the group for 5 years. He was in Menudo for 5 years. What we're trying to do here, this is the point of what we're trying to do. We're trying to figure out how strange is Ricky Martin. We want to know how different is Ricky Martin from the rest of the group. Now, if you remember, his deviation is 1.44. Well, what does that mean? That means that if we look at his tenure, how long he was in the group, 5 years, subtract the mean, which is 3.55 years, 3.56 years, right? Okay, then his deviation, whoop, there, where are you, Ricky? There you are. His deviation is 1.44 years. That makes sense, right? He deviates from the mean a positive 1.44 years. He's 1 year at 0.44 years more than the average. That's his deviation. If anybody has an average that's below the mean, so for example, Raymond Acevedo only had 3 years instead of 3.56 years, well, then that means that he deviates about negative 0.56 years, right? Below the mean, negative 5.56 below the mean. You're like, okay, great. Well, that's good. He's got more, right? He's not normal. He's strange. Well, but if you think about it, if you just look at the average and say, well, he's above average, does that really tell you how he is compared with the entire group? Because nobody here is right on average. Nobody is exactly on average. Okay, there's nobody who has 3.55882353. Nobody has that tenure. So everybody is a little bit strange. So what we're trying to do is figure out exactly how strange is Ricky Martin? Meaning, is it weird to have a deviation that is 1.44 years above the mean, right? Is it strange to have 5 years when the average is 3.56? And the way we do this is by figuring out what is the normal amount of deviation, okay? What is the normal amount of deviation? Now, if you remember, we had a problem with this. We would say, okay, well, then instead of just looking at the average years that you're in the group, let's look at the average amount that people deviate from the group, okay? Because, you know, if people don't deviate very much, then maybe 1.44 years is really, really strange. But if a lot of people deviate a lot, then it's not very strange. The problem with that is we cannot get the average deviation, because if you actually add up, excuse me, all the deviations, you're going to get 0. All the deviations added up, you're going to get 0. That means if you add up all the deviations and divide by 34, which is the total number of people who have been in Menudo, you're going to get 0, because it doesn't make sense to do that. So to get over that, we squared the deviations. Pardon me. We squared the deviations, and then we added those up instead. Okay? So that's where we were last time. We got this number right here, 196.4. That is the sum of squares. That is the sum of squares for the population. Okay, but remember, we're trying to get kind of like this average deviation, a normal amount that it is to deviate from 3.56 years, right? That's what we're trying to get. We're trying to figure out how strange is Ricky Martin if he is deviating 1.44 years. So what we do is we've got to calculate something called the variance. So let me show you the formula, and then we'll talk about it. It's going to be super easy, but there's one important aspect of this that we've not done before, and that is that the calculation for variance is going to be different depending on if we're talking about a population versus a sample. So if you remember, we're trying to get kind of like the average amount of deviation. So we squared everything, we got the sum of squares, okay? Well, it makes sense then if we were looking for something that's similar to an average, that we would divide by n. And when we have the population, that's exactly what we're going to do. But if we're looking at just a sample, we don't divide by n, we divide by n minus 1. Now, the reason why is because, remember, the entire purpose of this class is to understand what's going on in a population based off of just the sample. What we found is if you divide by n, right? If you divide by the n of the sample, divide by the number of people in the sample, you're going to overestimate things. The variance gets overestimated. So instead, we found that we should divide by n minus 1. It gives us a better estimate of what the variance is in the population. So let me make sure I'm totally clear about this. The next step of getting kind of what would take the place of an average amount of deviation is to divide by n. That makes sense, right? If it's for the population, then good. Go ahead and do that. Divide by n. But if it's for the sample, you divide by n minus 1. So here's my question for you. When we look at our data of Menudo, should I divide this sum of squares by n or n minus 1? I should divide this one by n because it is the whole population, all the members that have ever existed in Menudo, all of them. This is all the members of Menudo. So that means that for us to get the variance, what we do is we take this, the sum of squares, divided by n, and n in this case is 34. There's 34 who have been in Menudo. 5.576, so about 5.58. This is the variance. Variance. It is a score that means this is kind of how much the scores are varying in our distribution. All right? Let's look at our other data that we've been working on, which is these data, cups of coffee, remember cups of coffee, area code, hours of sleeping, liking for donuts, remember that? And specifically, we were looking at liking for donuts, right? And what we did was we squared them all. This is liking for donuts. This is x squared, not the sum of squares. Remember, we're looking at the sum of squares the different way. So those are all the deviations squared, and this is the sum of squares. So this is the sum of squares. So this is sum of squares. All right? If I want the variance, what am I going to do? So what I want you to do is calculate the variance. All right, to calculate this variance, this is a sample. It is not the population. So for us to get the variance, I'm going to put variance over here. Let's go ahead and make this a lot bigger. So just so you can see this a little bit better. So make this bigger. What we want to do is let's calculate the variance. Come on. Excel is being slow for me. Quit it, Excel. All right, let's try this again. Okay, so to calculate the variance, here's what we're going to do. We take the sum of squares. So variance is going to be the sum of squares divided by, not divided by n, because this is a sample. We're going to divide it by n minus 1. The total n is 7, so n minus 1 is 6. The variance for this sample is 8.29, essentially. That is variance. Variance is different when we're talking about the population compared to the sample. And the reason why is because we're trying to get at something like an average amount of deviation. Okay, what's the normal amount to deviate from the mean? If you've got the entire population, you just divide by n. If you don't have the entire population, you should do n minus 1 because otherwise you're going to overestimate or underestimate the amount of variance that's going to happen. Okay? So here's where we left off then. This is what we were looking at, the variance. Then, so if you look right here, we're going to get to standard deviation. Now we call standard deviation two different things depending on if you are looking at the sample or the population. This is a lowercase sigma, and so when we're looking for the standard deviation of the population, we call it lowercase sigma, right? And that is, you see this SS pop divided by n? Look, it's the same as variance, SS pop divided by n. It's the same thing. All we got to do is take the square root of that. We're taking the square root of it. Now we do that the same whether we're looking at the population or the sample. You just take the variance and you take a square root of the variance. That's all we're doing. That's all we're doing in either case. So the standard deviation